All right, welcome back to the last part of the wind lecture for Geography 101. So to continue on, we're going to talk about seasonal changes in wind. So not only do different atmospheric conditions change throughout the planet, but they also change with the seasons. So we can think about the ITCZ, the Intertropical Convergence Zone. Remember, is that low pressure system between the Hadley cells. And that low pressure system is formed as the sun heats up the equator more than other regions of the Earth. And so you have the heating of the planet there, and that warmth causes the expansion of the atmosphere and that low pressure. But of course, the angle of the Earth that receives the most sunlight changes throughout the season as the Earth orbits around the sun. And so that ITCZ shifts throughout the year. And so you can see here the ITCZ in July, this upper line, the average position, is further north than the ITCZ in January, which it moves south as the southern hemisphere is in summer. And this has a big effect on weather because remember the ITCZ is an area where you have upward movement of air and therefore cloud formation. And so that position of the ITCZ determines the weather for that region. We can see here as well, these are different wind maps, again with isobars, that the wind direction and power tends to change throughout the season as well. The left being the average atmospheric pressure in January and the right being in July. You can see here, for example, that you tend to have stronger high pressure in Asia during January compared to in July. Where this has the most significant effect, arguably, is in monsoon areas. So monsoons are strong seasonal winds in southern Asia that can bring heavy rain in summer and dry conditions in winter. And you might have seen images or experienced yourself these crazy strong flooding events that can occur in Asia or particularly in India and Southeast Asia during these monsoon events. And there's a very predictable pattern that actually in the atmosphere that causes these events. So first off, you have, in order to have a summertime monsoon with heavy rain, the ITCZ is going to shift northwards as the sun predominantly is hitting the Earth in more northerly areas. And as that ITCZ moves north, then you have the land warming up as well. And so that warm land causes the low pressure system of the ITCZ, and that low pressure draws in water vapor from the ocean, and that cool ocean air moves onto the land, and as it rises and gets sucked into that low pressure system, then it condenses and falls out as rain. So you can have a large amount of moisture moving from the ocean into this low pressure system, and therefore causing a lot of rain. And the opposite kind of happens in the winter when the ITCZ moves southwards and you have a high pressure system over the land. And so the rainfall is predominantly over the ocean instead of the land, as you have sinking air over the land instead of rising air. But besides these kind of large-scale events, we can have more local wind effects, such as sea breeze. You may live near the coast and have experienced these very pleasant sea breezes throughout the day. And the same kind of process that forms monsoons also causes sea breezes, but on a daily time scale instead of seasonal time scales. And so you have the land warming up during the day, causing a low pressure system, and that low pressure system draws in moisture from the ocean. And as that moist air moves into the low pressure system and gets lifted up, it condenses and that forms this circulation pattern of cool sea breeze moving towards the land. And the opposite true as the land cools off and forms a high pressure system. A similar situation happens in valleys for valley breeze. So usually mountaintops tend to warm and cool more quickly than valley floors, which have more vegetation. And so as the mountaintops warm up, they form a low pressure hot system, and that draws wind upwards. But as they cool at night more quickly, they form a high pressure, and so you have cool air moving into the valley. So if you've ever backpacked in a mountainous region, you always have to be careful not to, if you're going to spend the night in the valley, it's probably going to be pretty cold at night. An additional wind that's common in glaciated areas are called katabatic winds. And so these are really common in poles or near the Greenland ice sheet or Antarctica, where you have very cold conditions and a lot of elevation. And so because the Greenland ice sheet, for example, is so cold, you have a high pressure system forming. That air cools and gets pushed downwards and condenses, and then that high pressure system flows downhill. And because there's so much ice in Greenland, there's a lot of elevation to lose, and so that those katabatic winds can accelerate as they move down the ice sheet, and you can have extremely fast winds in these katabatic events. And generally, on an ice sheet or a large glacier, you're going to have the predominant wind direction being these katabatic winds that move downhill. Another wind event that have a number of different names: foehn winds, Chinook winds, Santa Ana winds. And these are winds that occur on the lee side of a mountain range. So the windward side is where you have moisture rising and a lot of moisture falling due to that adiabatic process. And then the leeward side is where you have dry air that falls downwards, and you don't have a lot of moisture in that air. And so that air can accelerate as it moves down the mountain, and because it's lost most of its moisture, it's very dry. And so Santa Ana winds in California have been associated with very bad fire weather and can spread fires very easily because they're so dry, and they're generally very strong winds that can push the fire really far. All right, and so the last thing that we're going to talk about for this lecture are El Niños and La Niñas. And so these are atmospheric and oceanic conditions that happen in the Pacific Ocean. And you can see here, these are sea surface temperatures during an El Niño event. And so in order to understand El Niño and La Niña events, we first kind of have to understand what are the normal conditions for atmospheric and oceanic circulation within the Pacific Ocean. And so in a normal condition, you have winds moving in the equator. They move westward and they draw in some of that deep, cold water up towards the surface. in the eastern Pacific near South America, and that warm air that's been warmed by the sun, or the warm water that's been warmed by the sun, kind of gets pushed off towards Asia in the West Pacific. And that is that pushing of the water is caused by convective circulation within the atmosphere, and that circulation pattern is called the Walker circulation. And generally, that process kind of looks like this. In an El Nino event, though, that circulation pattern can be significantly weakened or even completely reverse. And so instead of this circulation that's moving water eastward or westward, like here, you have the winds circulating in the opposite direction or just weakened. And so you no longer have that upwelling that we talked about in the previous lecture, and instead that warm water stays in South America and in the Eastern Pacific. And so as a result of that lack of circulation and the lack of that warm water being pushed towards Asia, you tend to have droughts in Asia, as you have colder oceanic conditions in Asia, as well as really extensive flooding and precipitation in South America and the Eastern Pacific, as you have more hot water in this region and therefore more evaporation and more rainfall. And so generally, because you have this warm water being spread over further regions of the Pacific, as well as less upwelling of cold, deep water from the ocean, you generally have warmer global temperatures during El Nino events. La Nina is pretty much the exact opposite. So instead of these Walker circulations being weakened or reversed, the normal conditions are amplified. And so you have extremely strong Walker circulation. And so you have these strong wind patterns that are moving the wind and the water really strongly westward, and that draws all of the warm water to Asia, and it brings up a lot of cold, deep water up in South America and Eastern Pacific. And as a result of all that upwelling and all that warm water getting pushed to Asia, you generally have droughts in South America, less evaporation there, and so less precipitation, as well as flooding in Asia, as you have more precipitation, warmer oceanic conditions in Asian countries. So these are events that have a big effect on global climate, and especially climate near the Pacific. And they are expected to get more significant with climate change. Climate change is the universal amplifier. And so we expect that that these kind of extreme El Nino events are going to be more common due to more energy in the atmosphere, and that could cause some even more extreme weather events, especially in South America. All right, so just to recap everything that we talked about in these last three parts of the lecture. We talked about what is wind and what wind maps look like. We talked about forces acting on wind and geostrophic and frictional balances. We talked about cyclones and anticyclones. We talked about the 3 different cells in the atmosphere, that Hadley cell, the Ferrel cell, and the polar cell. We talked about the jet streams and how that can affect climate. We also talked about hurricanes and monsoons. We talked about local weather events such as Santa Ana winds. And then lastly, we just talked about El Nino and La Nina events. All right, thanks for watching, and I'll see you all at the next lecture.